Hello, this is Miraj Patel, and today we're going to be starting Unit 12, which is all about solutions and equilibrium. And today we're going to be specifically be talking about solutions and some terms we have to know about solutions and why do solutions form solutions and stuff that affects solutions and dissolving rates. And so, moving on. So a solution is pretty much just a homogeneous mixture, and there's two terms for a solution. We have a solute and a solvent. So the solvent is the dissolving medium or the dissolver, so to speak. So what is the little stuff we're going to dissolve in? And then the solute is what's being dissolved. So in this case, it looks like we have water and some green powder or something like this. And then so the solute is being dissolved in this water, and so the solute would be the green powder, the solvent would be the water because the water's um, being what the little stuff is being dissolved in. And a good way to remember which one's which is solute is present in a smaller amount, solvent is present in a larger amount. And you can remember that by thinking that solvent has more letters and than solute, so it's present in more amounts. Or I remember that solute is less because solute sounds like cute, and usually little things are cute. And then solvent sounds like a big bad bully, so like solvent. And then solute, a little cute. That's how I remember it. So, or you could just use the letter trick. And then here are types of solutions. Solutions can happen with everything, but most of the time we think of liquids dissolving other liquids, but or solids and stuff. But it can happen with everything. Like gas can dissolve gas, which is a good example is air. And liquid can dissolve in gas, and a good example is water vapor in air. And then gas and liquid, it's like soda because the carbonation is dissolved in the liquid water and solution. Then liquid dissolved in liquid like vinegar, which is acetic acid in water. Then we can have solids and liquids, like most of you probably think of like salt water or Kool-Aid. And then we have solids and solids, which could be like stainless steel, so like chromium and nickel in iron. So there's all types of solutions, and gases, solids, and liquids can all dissolve in each other. And so why does stuff dissolve? And this all has to do with IMAFs. So IMAFs are very important in chemistry. And so normally there's IMAFs between the same substance. So here we have water. So notice how all the water molecules form IMAFs with each other. And then the solute also forms IMAFs with each other. So methanol is forming IMAFs with other methanol molecules. So here we have these IMAFs between the solutes here and then solvents here. And so these must break. So we must break these IMAFs. And IMAFs between solute and solvent must form. So pretty much you can think of it as we have one group here and one group here, and so pretty much they have to break their own connections and let the other intermix. So like they have to mix up, and so that's how we get how things dissolve. So because these IMAFs break just with methanol and just with water, and then they share IMAFs and they form bigger ones. And then something will dissolve more if they have stronger IMAFs between solute and solvent. So if they like to break up their own IMAFs with each other and form IMAFs with the solvent or in solute, that means they'll dissolve better. And then now we're going to be talking about electrolytes, which are types of solutions. So an electrolyte is a is electrolytes form ions to conduct like electricity usually in a solution. So when you hear of Gatorade has electrolytes, pretty much it has these ions that conduct electricity. So that means Gatorade would conduct electricity because it has a lot of electrolytes. And strong electrolytes are pretty much ionic substances that form ions. So think of ionic compounds like salt, so NaCl is a good electrolyte. And then non-electrolytes are molecules that like to stay together and don't form ions, like pretty much covalently bonded molecules or molecular compounds do not form ions. And then we're going to be talking about solubility. So there are things that affect how much of a solute can dissolve in a given amount of solvent at a given temperature. So solubility is a maximum mass of solute that will dissolve in a given amount of solvent at a given temperature. And so here we have several substances, and notice how there's different amounts of solute that's dissolvable in water, 100 grams of water at 20 degrees Celsius. So notice there's 36 grams of table salt, 9.6 grams of baking soda, and 203 grams of table sugar. And the cool thing is that even though this is such a big difference in number, 36 and 203.9, they both almost dissolve zero point 0.6 or 0.61 moles in water. So that's the cool part about that one. So, um, so if there's more substance that's able to be dissolved, that means it breaks its IMFs with the solute-solute molecules and solvent-solvent molecules and easily forms IMFs with the solvent and solute. So table salt and table sugar easily break up their own IMFs and form IMFs with the water that right now it's being dissolved in. And so now we're going to be talking about several types of solutions. So there's unsaturated solutions, which have less solute than the maximum capability. So think of like an elevator and a weight limit. So if it's unsaturated, that means we still have room for more solute, or we still have more room for weight on an elevator. So think of unsaturated as having less than the limit. Then saturated is the maximum limit, so maximum solute dissolved, so this is right on the maximum. And notice how there's barely any crystals forming extra. So think of an elevator and we have the maximum amount of people. And then we have supersaturated, which is more than the maximum solute dissolved. So this would be like an elevator filled to capacity and then even more weight. So this is like an elevator about to fall because there's too much weight in it. And so, and notice how in this supersaturated solution, there's a lot of crystals forming here. And so here are some pictures of real solutions. So here, because there's no crystals at all forming, this must be unsaturated, because notice how there's no crystals here, nor here. Then we have a saturated solution. So notice how there's little crystals forming. And so, just like this test tube, it has a few crystals forming. But then we have supersaturated, where there's tons of crystals forming because there's more solute than the liquid can dissolve. And now we're going to be talking about polarity in terms of solubility. So polarity is, how atoms either share or, hog electrons. So polar substances, if you remember, hog like electrons. So one side has a little bit more electrons than the other, so it forms positive and negative. Then nonpolar is the opposite; they share electrons equally. So remember that polar dissolves polar, so and then nonpolar dissolves nonpolar. So just think of like dissolves like. So if we have a polar substance, it can only dissolve in polar stuff. If you have a nonpolar substance, it can only dissolve in nonpolar stuff. And so here we have several molecules and their Lewis dot structures, if you remember from the unit about covalent bonding. And so here we have the diagrams, and so we can tell by these diagrams whether it's electronegative or polar or not. And so notice how CCl4 carbon tetrachloride has four chlorine molecules pulling away, so it's nonpolar because all these poles cancel each other out. So this is nonpolar. Water, I'm sure most of you know by now, is polar because this oxygen pulls these electrons from the hydrogens, which has a net force upward. So this is H2O is polar. And so C6H14 is like this. And because carbon and hydrogen have similar electronegativity, these are not carbon, hydrogen, or hydrocarbons are nonpolar, and so this is why these two aren't dissolving. So this is why this stack of liquids aren't dissolving, because we have a polar substance, nonpolar, sorry, CCl4 is nonpolar. Then we have a polar substance in the middle and a nonpolar again at the top. So pretty much uh, this polar substance is separating these two so they can't dissolve, because remember, like dissolves like. And the reason why like dissolves like is because there has to be similar IMFs. So remember, we have to break IMFs and form the same type of IMFs with the solute to solvent. So the solute and solvent both have to have similar IMFs so they can share each other. So these two, if we have C6H14 and carbon tetrachloride together, they would dissolve. But right now this water is separating these two, and so they can't dissolve. Because remember, like dissolves like, so these are both nonpolar, but this one's polar, so that's why it's split up. And so notice how we have uh, two bowls, and so notice how this substance here, it's dissolving, but this substance isn't. So you can tell that that these two, okay, if this is water, let's just assume, that means if it dissolves, it also must be polar, just like water. But this substance is nonpolar because it does not dissolve in water. So remember, so if it's polar and polar, like water and some other substance, then they dissolve. But the second one is polar and nonpolar, so they don't dissolve, and that's why it's separated and it floats at the top. And here we have solubility curves. So here are some pictures of some curves, and they sort of look like phase diagrams because they have like temperature on the bottom, and it's a graph. And so you can sort of think about it as a coordinate plane. And so we have these lines going across, and these are different substances. Notice their chemical formulas are written on the line or on top or beneath it. And so as we change temperatures, it tells us the amount of this substance that can be dissolved in 100 grams of water. So let's just say at 10 degrees Celsius, we can dissolve almost 30 grams of KCl. So pretty much that's how you read it. So you just look like a normal coordinate grid. So at 30 degrees Celsius, we can dissolve 10 grams here of KClO3. So you just go to the right and then go up and find your substance, and that's how much can be dissolved at that specific temperature. So here are some questions. Which one has the highest solubility at 20 degrees Celsius? And so we would first go on the x-axis, so temperature, and find 20 degrees Celsius, which is right here, and then find which one's the highest. So if we go up and see which one dissolves the most grams at 20 degrees Celsius, it would be NaNO3, so right here. And before we continue, I forgot to mention that each of these lines are saturation points. So at 20 degrees Celsius, NaNO3 would be saturated when we reach about 87 or 88 grams of solute in 100 grams of water. So these are all saturation points at various temperatures. So just remember that. So if something's above it, it would be supersaturated because it has more, like at 20 degrees Celsius, and we had 90 grams, because 90 grams in at that temperature and that 90 grams of solute in 100 grams of water, that would be saturated because that's more than the saturation point, which is 87 grams. So if if there's grams amounts above the line here, then it's supersaturated, and if it's below, it's unsaturated. So remember that. And if it's right on line, it's saturated. So at 20 degrees Celsius, 87 would be saturated. So what is the highest solubility at 30 degrees Celsius? So 30 is right here, so we go up all the way. And this orange line is all the way up here, so it's even off the chart. And so this CaCl2 has a high solubility at that point. How many grams of KClO3 can be dissolved at 70 degrees Celsius? So KClO3, which is right here, 70 degrees Celsius right here. So at about 70 degrees Celsius, maybe 30 grams should dissolve, for that saturated. Is 50 grams of KCl at 50 degrees Celsius saturated, unsaturated, or supersaturated? So 50 grams at 50 degrees Celsius, 50 grams at 50 degrees Celsius. So that's right here, and KCl is down here. So remember, I told you that these lines are saturation points, so if there's something above it at that particular temperature, so at 50 degrees Celsius, 50 grams is above the line, so this would be considered unsaturated or supersaturated. So think of like Superman flies high in the sky, so it would be supersaturated because above, like above and beyond, so Superman. And then, is 30 grams of NaCl at 30 degrees Celsius saturated, unsaturated, or supersaturated? So 30 grams of NaCl, which is right up here, so this black line, 30 grams is down here. So if it's not above, or like Superman, so not flying above, and it's below the line, it's unsaturated, because this is a saturation point, which would be about 35 grams, so it's 30 grams, so it's below. And then here we're going to be talking about rates of dissolving. So we're going to be talking about solids dissolving in liquids and gases dissolving in liquids. So solids dissolve faster when we have more surface area or small particle size. So if you ever have if you ever dissolve like anything, and if you crush it up, because when you crush it up or have small particles, it has more surface area, and so the substance would dissolve faster than if we left it as a big clump. So if we have sugar cubes and we crush up, we have fine sugar, or we have sugar cubes, the fine sugar will dissolve faster because it has more surface area for the water to hit it and dissolve. And then if we, so notice how this one large cube has less surface area than all these cubes, and they both have the same mass. So this will dissolve faster because there's simply more area for the water to start dissolving. And then if we have more stirring, so if you ever, dissolve something, we stir things so it dissolves faster, because when we stir, the water or solvent hits all the parts of the solute and it dissolves faster. And also, if we have a higher temperature, things will dissolve faster, because if you think about just like kinetic molecular theory, if things are moving faster, so if the solvent is moving faster, they'll hit the solute more often, and it'll be easier to dissolve. And so notice how this just sounds just like kinetic molecular theory or reactions. So notice how, remember, reactions react when there's more surface area, more stirring, or higher temperature. And just think of collisions. So same thing in dissolving. Collisions have to happen between solute and solvent. And so if we have more collisions, we will have more dissolving, or dissolving will happen faster. But this only happens with solids. Gases are weird, and so gases dissolve faster when there's no stirring, high pressure, and low temperature. And so notice how no stirring and low temperature are exact opposites of what I said with the solids, but high pressure is not opposite, it's just special. And so the reason why no stirring gas dissolves faster when we have no stirring is because if you think about soda, when we stir or shake up a soda, all the gas gets out of the soda. So stirring pretty much like moves around the gas, so the gas gets to the surface and gets released. So stirring is not what we want. So just think about soda. So you don't want to stir sodas, and so if you leave the soda alone, that means the gas will stay in. And then high pressure, the reason why that helps dissolve is because if we force the gas or put pressure on the gas, that means it will stay closer to the liquid and dissolve, and we pretty much like force it in there. So that's why sodas are pressurized, so we can dissolve the gas and keep it in there. And then the last reason why we store gas or soda at cold temperatures because it helps dissolve the gas and prevents it from going flat. And so the reason why is if we have lower energy for the gas will be moving slower, and the gas will stay in the liquid longer. And that's why we store soda in cold areas, and we don't really try to stir soda unless you really want flat soda, which I'm not sure. I'm sure most of you wouldn't want. And that's also why we have soda at high pressure, so pretty much the gas dissolves better. And so here's a quick quiz to see what you learned. Compounds that partially dissociate or ionize into solutions of ions and molecules that partially conduct or electricity are non-electrolytes, weak electrolytes, C, strong electrolytes, or D, Gatorade. And it's definitely not just Gatorade, because Gatorade is not just, we're just talking about electrolytes here, so it's not Gatorade. Is it a non-electrolyte? Well, it says that they partially dissociate, and non-electrolytes don't dissociate at all. So it's not A. And then let's eliminate down to weak and strong. So compounds that partially dissociate into solutions of ions. So pretty much, do they, if it partially dissociates, it's some ions are forming, so it'll conduct some electricity, but not as much as strong electrolytes, because strong electrolytes, if I remind you, are like ionic compounds that fully dissociate in water. So that's strong electrolytes, so, but this is partially dissociate, and that's pretty much the key word, and so from that you can figure out that it's a weak electrolytes that partially dissociate. And then non-electrolytes don't even dissociate at all, so that's what non-electrolytes are. And then polar water molecules will not dissolve in A, polar alcohol molecules, B, most ionic compounds, C, nonpolar fat molecules, D, partially ionized acetic acid molecules. And so if you remember, like dissolves like, polar will dissolve in anything but nonpolar. So uh, C um, says that polar water will dissolve in non-polar stuff. But if you remember, like dissolves like, so polar and non-polar are definitely opposites. So polar water will not dissolve in non-polar fat. So that's how, if you did not know the other answer, that's how you could figure that out. But just FYI, like dissolves in like, so polar will definitely dissolve in polar. But these two, B and D, don't talk about polar, they talk about ionic stuff, ionic compounds. But uh, I didn't tell you this, but polar stuff can also dissolve in ionic compounds because polar and ionic both have uh, poles on their compound, so they have a slightly positive and negative ends. So these two are practically the same when we're talking about IMAF. So polar and ionic are the same. The only thing that's separated is like nonpolar. So nonpolar won't dissolve with ionic or won't dissolve with polar. So think of nonpolar by itself, so no charge differences, and ionic and polar in one group. For a given substance, which of the following will not influence how fast it dissolves? A. Temperature. B. Amount of agitation. C. Molar mass. Or D. Size of crystals. So you can think of about amount of agitation as stirring. So it should be temperature, stirring, molar mass is the same, and then size of crystals could be the size of the solute. So which of the following will not influence how fast it dissolves? So temperature, we remember that solids do dissolve faster in higher temperatures, so temperature definitely affects something. Stirring, if you remember, stirring causes more collisions, so it dissolves faster. That definitely affects it, affects dissolving rates. And then size of crystals, or the size of the solute particles, does affect it because we know that larger crystals have a harder time dissolving because there's less surface area. So the only one that doesn't affect how fast it dissolves is molar mass. So C is the incorrect one, or correct answer. And so molar mass has nothing to do with how fast it dissolves, because molar mass is just how much one mole weighs, or how many molecules, are in the molecule, so how much does it weigh. But that has nothing to do with how fast something dissolves. Solubility of a gas in a solvent is affected by A. Both temperature and pressure. B. Only pressure. C. Only temperature. So solubility, which is how fast something can dissolve, and remember this is a gas we're talking, so just think about a soda. Where do we store sodas? We store sodas in usually refrigerators after you open it, and we also we don't want to stir shake a soda, and also soda bottles are pressurized, because that's why when you open a soda bottle you have to let out that gas because it's pressurized. So why do we do that? And the whole reason why we store sodas in cold areas and why it's pressurized and why we don't want to stir it is because it affects the solubility of the gas in the soda. And so we like sodas in cold areas because it keeps the gas down, in the drink. And so temperature definitely affects it. So B is out because it only mentions pressure. And then sodas are also pressurized so that the gas will stay in there because the high pressure sort of pushes it down. So definitely pressure also affects it. So the correct answer is both temperature and pressure. And if we had to add one thing, we can add agitation definitely affects it, because that's why we don't shake up sodas if we want to keep it carbonated. So so those are the three things that affect gas, is dissolving in liquids. And so that is it for today. And today we talked about solutions, solutes, solvents, electrolytes, and we talked about things that affect dissolving rates. And so the next video is all going to be about converting from moles of solute to like liters of solvent and stuff like that. And then we might also talk about dilutions and how to like diluted versus concentrated solutions. And so I'll see you later. And again, I hope this helped you, and I hope you have a good day.